Dear students, again welcome back for the sixth session for the solution chapter. So previously we have started the second part of the liquid solution called as liquid solutions. That is a perfectly homogeneous mixture of a liquid solute in the liquid solvent refers to which solution? Liquid solution, or it is also called as a liquid mixtures, or sometimes it is also called as a binary solution. Okay, binary solution of liquids. Okay. So there we have considered the main thing is about the vapor pressure. So that we have discussed indirectly in the form of which one? Rolle's law. So what that states actually, what is first vapor pressure here? It is the pressure exerted by the vapors of the liquid that has been present above the surface of the liquid in contact with its own liquid. Means any liquid on its surface always has its vapors. Those vapors will create a pressure on the surface, and that particular equilibrium pressure is indirectly called as the vapor pressure. Or we can define that in another way also. What's that? As if we know that the surface molecules are highly unstable because they absorb the heat from the surroundings such that the liquids start to get vaporized. That is the process called as rate of vaporization. Okay. So at the same time, the vapors also gets condensed in the form of liquid into the liquid taken in the container. So that is called as condensation of the vapors of the liquid. So as these two processes are occurring simultaneously and then spontaneously along with reversibly, don't make the word as a spontaneous here, it is the reversibly first. So what happens there? Rate of vaporization of the liquid, when it is exactly equal to rate of condensation of that particular vapors of that particular liquid, there creates one pressure at the junction, and that pressure is called as saturated vapor pressure, or simply it is first called as vapor pressure. Usually we know that increase in temperature always increases the vapor pressure of the liquid. As the vapor pressure is more, means the liquid is having the low boiling point. Means less amount of heat is required to evaporate a liquid, means it is having the low boiling point. Low boiling point means it is having the higher volatility. Means increase in temperature increases the vapor pressure of the liquid, increases the volatility of the liquid, but decreases the which point? Boiling point. Now, as if we are not concentrating only on the single liquid component, it's a mixture of the two liquids. So if I take individually the two liquids, every liquid has its own vapor pressure at the junction in the pure state before start mixing. What happens when one liquid gets mixed with the another? It forms a liquid solution, no doubt first. Then what is the pressure on the vapor pressure that has been exerted at the junction of that particular solution now? It is not the liquid here, it is the solution. It is not the single vapor pressure of the liquid, it is the partial vapor pressure of the two liquids called as, for example, A and B. And that partial vapor pressure of the liquid is equal to the product of the vapor pressure of that liquid in its what state first? Pure state into its respective what fraction? Mole fraction. Means the pressure or the partial pressure, vapor pressure of the surface of the liquid at the surface of the solution or above the surface of the solution is equal to the product of the vapor pressure of that particular liquid into its respective what fractions? Mole fractions. Mathematically, we have mentioned that in the form of Pa is equal to Pa naught into Xa and Pb is equal to Pb naught into Xb. So these are called as Pp's of the liquids which and which? Two liquids called as A and B. What is this? Vp's of the two liquids called as which and which? A and B. Then what is Xa and Xb? Here they are called as mole fractions of the two liquids called as which and which? A and B. That is, the partial vapor pressure of one of the liquid in the liquid mixture is always equal to the vapor pressure of that liquid in its pure state into its respective what fraction? Mole fraction. Okay. Then after these two, the total of these two is considered to be the application of indirectly the what? the Dalton's law of partial pressure. Means the total pressure exerted with a mixture of the non-reacting gases is always equal to what? Sum of the partial pressures of the individual liquids are with the gases that we have taken. Okay, that is the indirect application of what? Dalton's law. Okay. Now, this particular liquid solutions are of two types. One is an ideal solution and then the non-ideal solution. Ideal solution and then the non-ideal solution. What's that ideal solution here? A solution which obeys the Rolle's law at all the conditions of temperatures and concentrations is called as what solution? Ideal solution. As if I have already mentioned, it is similar to that of which gas? Ideal gas. What is that ideal gas? A gas which behaves or which obeys all the gas laws under all conditions of temperatures and pressures is called as an ideal gas. Instead of gas, we are using the what? Solution. The solution which obeys the Rolle's law at all the conditions of temperatures and pressures means it is called as what? The ideal solution. No solution again is perfectly ideal. There is no solution strictly found to be the what? Ideal. Similarly, we have mentioned the same thing. What is that? No gas is perfectly ideal in the nature because all the gases are considered to be the real gases here. Non-ideal gases. Means just the ideal gases are imaginary. They are just found to be what? Imaginary. So similarly, no solution is perfectly ideal, but a solution can be ideal if and only if. IFF means it is if and only if the solution is very dilute in nature. Means we can make the solution to be ideal in nature if and only if it is found to be what in nature? The ideal. Sorry, very dilute in nature. Means we have to have a very smaller amount of a solute with added with a large excess of a solvent refers to the what solution? Dilute solution, and particularly that particular liquid dilute solution is an example for a what solution? Dilute solution. So for example, benzene and toluene, they are the examples with respect to example. Benzene and toluene. Ethyl chloride and ethyl bromide. Chloroform and then the bromoform. N-hexane and M-neptane. What these are? They are some of the examples with respect to that ideal solution. Suppose if I take 50 ml of benzene and 50 ml of toluene, means it is not an example for an ideal because it is not a dilute solution here. If and only if the solution means if benzene is found to be very less in amount as compared to that of the toluene that we have chosen or the taken, then it is found to be an example for an ideal. Okay. So then what are the characteristics that we have observed here? What are the characteristics with respect to ideal solution? The first one is it obeys Rolle's law at all the conditions of temperatures and then the concentrations. It obeys what? The Rolle's law at all the conditions of which and of which? Temperatures and then the concentrations. So then it satisfies Pa is equal to Pa naught into Xa and Pb is equal to Pb naught into Xb, means it has to satisfy, or it has to satisfy Pd must be equal to Pa plus which one? If that be the case, then we can say that it is an example for a what? Ideal solution. Then interactions of individual liquid components. Individual which one? Liquid components. What are those? Components. What is that? Either A dot dot A or B dot dot B is same as A dot dot B interactions. If that be the case, then we can say that it is an example for a what solution? Ideal solution. Means two liquids have same structure and then same polarity. Means if the individual interactions is similar to that of the mixed interaction, means they must have the similar structure and then the similar polarity. If that be the case, then we can say that the solution can obey the what laws? Raoult's law. Then, no change in volume before and after mixing the two liquids. That is indirectly, mathematically we will mention that in the form of delta V mixing is equal to what? 0. Means there is no change in the volume before and after mixing of the two liquids. And finally, no enthalpy change with respect to which one? No enthalpy change during the dissolution of a one liquid with respect to another liquid, that is delta H of mixing is also equal to what? 0. If thus be the case, we can say that this is an example for a what solution? Ideal solution. Okay. So I think this already I have explained in the previous briefly now. Okay. So then how to write the graphical representation with respect to the which one? Graph for the solution of which one and which? It is the ideal solution. Next, we will have the graphical illustration or the representation with respect to the Raoult's law. Graphical representation to show an ideal solution, which obeying the what laws? Indirectly, the Raoult's law here. So here, this is called vapor pressure. What's that? It is the vapor pressure along this one, and this is the mole fraction that is called as X. Mole fraction that is going to be the X. So here the thing is, as if we are having two different liquids. Let us consider two liquids as A and B, XA and then XB. It is 1 for example. Therefore, this must be 0, because we know that in a liquid mixture consisting of a solute and then the solvent, the sum of the mole fractions is always equal to what? 1. Means if this is 1, mole fraction of XA is equal to A is 1, means B must be equal to 0. As this one, what happens? XA must be equal to 0 and XB is equal to 1. Again, the means here, as mole fraction of A goes on decreasing, means the mole fraction of A goes on increasing, such that their sum must be equal to what exactly? 1. Sum must be exactly equal to what? 1. Okay. So let us have, we know that PA is equal to what? PA naught into what? XA. And PB is equal to PB naught into which one? XB. So here, as we know that PA is equal to, as mole fraction of A goes on increasing means, from XA is equal to, first let us take XB here, first XB, let us take this one. As XB from 0 to 1 increases, means XB increases, means whatever the PB, the vapor pressure of that goes on increasing. Let us have this. This is called as PB. What is PB here? Partial pressure of the liquid B. As we know that XB is equal to 0 and ended with XB is equal to 1, means the mole fraction of B goes on increasing. As the mole fraction of B increases, means the partial vapor pressure of that particular liquid B goes on increasing. And if this is 1, means PB is equal to PB naught. XB is equal to 1 means what is that? PB is equal to PB naught. Therefore, this is called as PB naught. What is PB naught here? The vapor pressure of the pure liquid in its what state? Pure state. So, what is small pb here? It is the, let's write this as PB here first. What is small pb here? It is the vapor pressure, partial vapor pressure of the liquid P. It increases with increase in its what fraction? Mole fraction. Xa is equal to 1 first. X is equal to 1. Xi is equal to 0 means the mole fraction of A goes on decreasing. Means as Xi decreases means what about the PB? Pa also decreases. Means it is found to be the maximum initially. Let us choose this one first. Xi is equal to means this is called as Pa naught. Why it is called Pa naught means if Xi is equal to 1 means Pa must be equal to what? Pa naught means the mole fraction, vapor pressure of the liquid is exactly equal to its partial vapor pressure if Xi is equal to what? 1. As Xi goes on decreasing means whatever the Pa, this also goes on decreasing. Okay. So here this is PB naught and this is Pa naught and this is found to be the Pa. What is Pa here? It is the, let us write this here to make very clear. This is Pa, partial pressure of A goes on decreasing because the mole fraction of A goes on decreasing. This is partial pressure of B goes on increasing because the mole fraction of B goes on increasing. Okay. Now, this is called PT. What is PT? Total vapor pressure, which is equal to Pa plus PB. According to what law here? According to the Dalton's law of partial pressure, because the total pressure exerted by the mixture of vapors of the two non-reacting gases is always equal to its sum of its mole fraction. Therefore, PT must be equal to which one? Pa plus PB. So this is called as the graphical representation to show in what behavior? Ideal behavior. Okay. So that is about that. So here why we are not writing that in the exact straight lines or the exact curves? It is mentioned only in the form of dotted, means that shows that it is going to be the ideal solutions are found to be what in nature? Imaginary, because we can't write that in the straight with the perfect lines. Just we had mentioned that in the form of only the dotted lines. That shows that the solutions of ideals are usually what in nature? Imaginary. The same thing that we are expecting in case of the graphical representation. Okay. So next is, what is non-ideal solution? Now, just the dead opposite, that's it. The solution which doesn't obeying or doesn't obeys the what law? Rolle's law at all the conditions of temperatures and concentrations, then it is called as what solution? Non-ideal solution, or it is also called as sometimes real solutions also. Okay. So that is, we can make this, okay. Any solution which doesn't obey the Rolle's law at all the conditions of temperatures and concentrations means it is called as what solution? Non-ideal solution. Again, the characteristics of a non-ideal solution. Non-ideal solutions. Just they are opposite, that's all. It doesn't obey Rolle's law at all the conditions of temperatures and concentrations. It satisfies PV not equal to this and PB not equal to this, PT not equal to PA plus PB. Or indirectly, doesn't satisfy PA is equal to PA not into XA, PB is equal to PB not into XB, or PT is equal to PA plus PB. If it is, doesn't. If it satisfies means PA not equal to PA not into XA, PB not equal to PB not into XB, and PT is not equal to PA plus PB. Interactions of the individual liquid components either A dot dot A or B dot dot B is always different. Is always going to be the what? Different as that of A dot dot B. Similarly, two liquid solutions have the, instead of same structure, we will have the different structure. If it is having a different structure means it is having a different polarity. Due to the difference in the structure and the difference in the polarity, the interactions of the individual liquid components is always found to be the different as compared to that of the mixture component, for example, A dot dot B. Okay. Then there is a change in the volume means delta V mixing is not equal to 0. Maybe greater than 0 or it may be the not. Then there is some absorption of heat or it may be the liberation of heat means delta H mixing not equal to what? 0. So just it is the opposite. This we can make the differences between a which and a which solution, ideal and then the non-ideal solution. Ideal solution means obeys the Rolle's law. Here it is, it doesn't obey the Rolle's law. It satisfies PA is equal to PA naught into XA and PB is equal to PB naught into XB. In case of non-ideal, it doesn't satisfy PA is equal to PA naught into XA and PB is equal to PB naught into XB. Then interactions of the individual liquid components is similar to that of interactions of the mixed liquid components. But in case of non-ideal solution, interactions of the individual liquid components is going to be the different as compared to that of the interactions of the mixed components. Then the structure and the polarity of the two liquid components are found to be same, but here the structure and the polarity are found to be different with respect to different for the two different liquids. There is no change in volume before and after mixing of the two liquids, but here there is a change in the volume before and after mixing of the two liquids. Then there is no heat liberated or it may be the absorbed during the mixing of the two liquids, but here there is either an absorption of heat or it may be the liberation of heat during the mixing of the two liquids. So these we can make out some of the differences between the what and a what. Ideal and then the non-ideal solution. Now we come across with the two different concepts. What is that? Not equal means we can have the two possibilities. Not equals means either we can have this or it may be the this. Whether that value must be greater than or it may be sometimes less than. Based on that, we are having the two different types of non-ideal solutions. Now the non-ideal solutions are of two types. What are those? Non-ideal solution showing a positive deviation and the non-ideal solution showing a what deviation? Negative deviation. Okay, so that we will discuss right now. So types of what solutions? Non-ideal solutions. Types of non-ideal solutions. Types of non-ideal solutions. The first one is NIS. What is NIS? Non-ideal solution. Showing a positive deviation. Positive deviation. The second one is non-ideal solution showing a negative deviation. Negative deviation. First, what is non-ideal solution? A solution which doesn't obey the what law? Rolle's law. At all conditions of temperatures and pressures. A solution in which the observed vapor pressure is greater than calculated from the Rolle's law is called as what solution? Non-ideal solution showing the what deviation? Positive deviation. Means any solution in which the observed vapor pressure is going to be greater as compared to that of which one? The positive deviation. As compared to that of the value calculated from the Rolle's law means it is called as positive deviation. The same thing here. Is lesser than expected from the which one? The Rolle's law, that it is called as non-ideal solution is solution showing a what deviation? Negative deviation. So just first it is the definition. What is non-ideal solution showing a positive deviation? A solution in which the observed vapor pressure is going to be greater than as calculated with respect to the what law? Rolle's law means it is a non-ideal solution is showing a what deviation? Positive deviation. The same solution in which the observed vapor pressure is going to be what? Instead of greater, it is lesser than calculated from its respective Rolle's law means it is a non-ideal solution showing a what deviation? Negative deviation. Then we can have the differences between these two. This itself is the first difference first. Here, PA is greater than PA naught into XA and PB is equal to, PB greater than PB naught into XB. Here, PA is less than PA naught into XA and PB is less than PB naught into XB. If it is equal, then it is a non-ideal, only the what solution? Ideal solution. If it is not equal means it is a non-ideal solution. But here, instead of not equal, it is mentioned as greater. Greater means it is showing a what deviation? Positive deviation. Instead of not equal, if it is less than means then it is going to be the what? Which one? The solution showing a negative deviation. Then PT is greater than PA into PB, PA plus PB. Here, PT is greater than PA plus PB. What's the meaning of that? Less than, As it is greater than means it is less than PA plus PB. Means it also doesn't obey the what law here? The Dalton's law of partial pressure, because the expected or the observed vapor pressure is going to be as greater or sometimes lesser. Greater means it is a positive deviation, lesser means it is a negative deviation. Then, interactions of individual liquid components like A dot dot A are B dot dot B is greater than A dot dot B interactions. Similarly, is lesser than this one. What have you mentioned in case of the previous? If interactions of the individual liquid components, if it is exactly equal to the interactions of the mixed component, then it is called as ideal solution. If it is not, means it is called as non-ideal solution. If instead of not, if it is greater, interactions of the individuals is going to be greater compared to that of the mixed component interactions, means it is a non-ideal solution showing a what deviation? Positive deviation. Same thing. The interactions of the individual liquid components is going to be less as compared to that of the mixed interactions, that is A dot dot B, then it is going to be a non-ideal solution showing a what deviation? Negative deviation. Okay. So now, delta V mixing is equal to 0, greater than 0. Here, delta V mixing is less than 0. What's the meaning of that? If I mix the two liquids, for example, let us take 100 ml of A, let us take 100 ml of B. There are three different possibilities here. This is AB solution, this is also AB solution, this is also AB solution. This is liquid A, this is liquid B. If the total volume is going to be 200 ml, this is called as V1. V1 is equal to 200 actually. This is going to be the V2. What is V2 minus V1? 200 minus 200 means it is equal to 0. Delta V mixing is equal to 0 means first it is an example for an which solution? Ideal solution. So here, if I mix these two, what happens? So the total volume with respect to that one is going to be 202 4.8. What's the difference here? Final minus initial. What is 202.8 minus 200? It is 2.8. 2.8 means it is plus. Therefore, it is a non-ideal solution showing a what deviation? Positive deviation. If I add these two, if I get 198.6, What's the difference here? What is final minus initial? That is 198.6 minus 200 means it is going to be the minus 1.4. Minus 1.4 means it shows a what deviation? Non-ideal solution showing a what deviation? Negative deviation. Means delta V mixing, if it is equal to 0, then it is an example for an ideal solution. Delta V mixing not equal to 0 means it is a non-ideal solution. Suppose if the delta V mixing is equal to greater than 0, then it is found to be the positive deviation. If it is found to be less than 0, then it is. So here V2 must be greater than V1. Here V2 is less than V1 because delta V is equal to V2 minus V1. When I am getting the value greater than 0, if V2 is greater than V1. When I am getting the negative here, if V2 is less than V1. Then delta H of mixing is greater than 0. Delta H of mixing is less than 0. What's the meaning of that here? Here, heat is absorbed during the dissolution of one liquid with the another. Absorbed. Means it is endothermic. It is indirectly endothermic. Here, heat is liberated. Heat is liberated means it is an example for an exothermic dissolution. If that be the case, it is an example for a non-ideal solution. If heat is absorbed, then it is called positive deviation. If heat is liberated, then it is called as negative deviation. Suppose there is no enthalpy change, means it is an example for a ideal solution. Okay, so that is delta V mixing is delta H mixing is greater than means it is the process is going to be the exothermic. If delta H mixing less than 0 means it is an example for an exothermic. Endo means it is positive deviation, exo means it is negative deviation. Then it shows minimum azeotropic mixture or forms minimum azeotropes or tropic mixtures. Here it forms a maximum azeotropic mixture. So that I will discuss later, because when you know the concept called as azeotropes. Okay, so that the last point that we will discuss later. Okay, so here another thing that is already we have entered this one, the boiling point. The vapor pressure is going to be the greater. Okay, so these are some of the differences with respect to which non-ideal solution showing a positive deviation and then the negative deviation. So here the solution in which the observed vapor pressure is going to be greater as compared to that calculated from the Raoult's law means it is called positive deviation. Suppose if it is going to be the lesser means it is a negative deviation. As if it is showing a positive deviation means the observed vapor pressure PA is greater than PA naught into XA and PB greater than PB naught into XB. With respect to negative deviation, PA less than PA naught into XA and PB less than PB naught into XB. And then we know that the PT, total pressure, is equal to sum of the partial pressure called as PA plus PB. But as if PA is more, PB is also more, what is the total pressure also? That also gets more. Means PT is greater than that of PA and then the PB, whereas in case of a negative deviation, it is PT less than PA and PB. So here, the interactions of the individual liquid components like A dot dot A or B dot dot B is going to be always greater compared to that of the mixed interactions between the liquids called as A dot dot B. Whereas, if it is found to be the lesser means it is found in a negative deviation. Then, there is an increase in volume during the mixing of the two liquids. How to show that there is an increase in the volume? Final volume must be greater than that of the initial volume. When the final volume is greater than that of the initial volume means if V2 is greater than V1, our delta V mixing is going to be the greater than 0. Then, if the volume gets a decrease during the mixing of the two liquids means it is found to be the delta V mixing less than 0 where V2 is less than V1, that is why it is showing a what deviation? Negative deviation. Next, during the mixing of the one liquid with respect to another, if heat is absorbed, then delta H mixing is equal to 0, therefore it is a what deviation? Positive deviation. Suppose during the mixing of the two liquids, if heat is liberated, then it is found to be the exothermic, therefore delta H mixing, if it is found to be the less than 0, it is called as negative deviations. Then finally, it forms a new type of mixture called as the minimum azeotropic mixture, and that forms a what mixture? Azeotropic mixtures. Okay, so the last 2 points that we will clarify after some time. Okay, so next is the graphical representations. Graphical representation with respect to the non-ideal solution showing a what deviation and a what deviation? Positive deviation and then the negative deviation. So next we will have the graphical representations. Representations of, first one, non-ideal solution showing a positive deviation. Second one is a non-ideal solution showing a what deviation? Positive deviation. Let's have the same thing here. Okay. So here we are having the vapor pressure against the what fraction? Mole fraction, that is going to be the X. Here also the same thing. Vapor pressure against the what fraction? Mole fraction, X. Okay. So let us take a chance in the form of if Xi is equal to 1, then Xb must be equal to 0. If Xi is equal to 0 means Xb must be equal to 1. Here the mole fraction of A goes on decreasing, whereas the mole fraction of B goes on increasing. Now the same thing. Xi is equal to 1, Xb is equal to 0, Xi is equal to 0 and Xb is equal to 1. Same thing. That's what we have written in case of the which one? The ideal solution. Let's have the same graphs first. As vapor pressure of A is maximum means the partial vapor pressure is also found to be the dependent, but it is found to be maximum at the initial and it goes on decreasing, because as Xi decreases means partial pressure gets decreased. Let us call this as PA naught. What is PA naught here? It is the vapor pressure of the pure liquid, because if Xi is equal to 0 means Xi is equal to 1 means Xb is equal to means there is only the one liquid but not the second liquid. Now it gets decreased like this. This is called as PA, I think. What is PA? Partial vapor pressure of A goes on decreasing as the mole fraction of A goes on decreasing. As we know that mole fraction of B is 0 means the vapor pressure of that one is also found to be 0. Then Xb is equal to 1 means it is going to be the maximum, therefore we can have the vapor pressure is going to be the increasing. Therefore, the next thing is, this is PB naught. What is PB naught? Vapor pressure of the pure liquid B in its pure state, and this is PB. And these two gets interacted, we can get the P total. This is called PT. This is PT. Okay. So now it is an ideal solution. The same thing I will write with respect to which one? Another time I will write for the second one, which shows a negative deviation now. This is PB naught, this is PA naught, this is PA, this is PB, and this is PT. So this is first the ideal solution, because it satisfies the what law here? The Raoult's law. But let us take now. If it is showing a positive deviation, the observed vapor pressure is going to be greater as calculated from the Rolle's law. That is, PA must be greater than PA naught into XA and PB must be greater than PB naught into XA. On that basis, I will observe the same thing like this. So here, now instead of this becomes a PA and then the PB now. This is PA, this is PB. So this is found to be the calculated from that of what law here? Rolle's law. But we are having the higher value compared to that. Means just it is above to the normal imaginary line of vapor pressure. So this is normal again. This is found to be the above that one. Therefore, PA is greater than PA naught into XA, PB greater than PB naught into XB. If that be the case, what is total also? That is also maximum. Therefore, we can have write this. That is, PT greater than PA plus P. Therefore, this is called as a graphical representation for the non-ideal solution showing a what deviation? Positive deviation. Non-ideal solution showing a what deviation? Positive deviation. So, same we can have the opposite. The observed vapor pressure is found to be less as compared to that of which one? The vapor pressure calculated from the Rolle's law. It is called as a non-ideal showing a what deviation? Negative deviation. Therefore, just it has to be written below like this. I think this is called as PA. This is now below again. This is PB. If these two are lower, means this is also lower. Therefore, this is called as PT, that is equal to PA plus PB. Here, the observed vapor pressure is found to be less than or PT less than PA plus PB means it is a solution or a non-ideal solution showing a what deviation? Negative deviation with respect to the what behavior? Ideal behavior. The imaginary or the dotted lines represents an ideal solution. Apart from that, we are having the thick lines. We are calling that as, if it is above that particular graph or the imaginary line, then it is called as a non-ideal solution showing a what deviation? Positive deviation. If it is written below that, then it is going to be a non-ideal solution showing a negative deviations. So this is done. These three graphs that you have to be very perfect, because each graph will carry 2 marks. Just the graphical write the graphical representation with respect to first one. Either they can ask the ideal solution. So the second one is a non-ideal solution showing a positive deviation or non-ideal solution showing a what deviation? Negative deviation. Okay, so these graphs we have to be very perfect. Okay. Now we are left with the last point in the form of azeotropic mixtures. Or that? Azeotropic mixtures. What are azeotropic mixtures? The examples related to this non-ideal solution showing a positive deviation is ethyl alcohol and water, ethyl alcohol and acetone. They are the best examples. With respect to non-ideal solution showing a positive negative deviation means any mineral acids with water is the best example for a non-ideal solution. For example, HCl with water, HNO3 with water, sulfuric acid with water, chloroform with acetone. They are the best examples related to what deviation? Negative deviation. Okay. So now I left with only the last concept for the liquid-liquid solution called as azeotropic mixtures. What are azeotropes? Azeotropic mixtures. Okay. Azeotropic mixtures. These are the liquid mixtures. These are the what mixtures? Liquid mixtures, which boils at a constant temperature, which boils at a constant temperatures without the change in their chemical composition. Without the change in the what composition? Chemical composition. Then those type of liquid mixtures are called as what mixtures? azeotropic mixtures. Here, azeotropic mixtures are the liquid mixtures which boils at a what temperature? Constant temperature without the change in the what? Chemical composition. Means, very simply, the constant boiling liquid mixtures are called as azeotropic mixtures. What is that? The constant boiling point liquid mixtures are called as azeotropic. Why they are constant? Means their chemical composition doesn't change. As if that be the case, it is called as what? The azeotropic mixtures. So these are of two types. One is minimum azeotropes or azeotropic mixtures, and then the maximum azeotropes. Maximum azeotropes. So what is the meaning of that particular minimum azeotropes and then the maximum azeotropes? These are the LMs. What are the LMs? The liquid mixtures, which shows a larger positive deviation from Rolle's law is called as which one? The positive, which shows a larger positive deviation from the Rolle's law, means it is called as minimum azeotropes. The same thing, the liquid mixtures which shows larger negative deviation. What deviation here? Negative deviation from the ideal behavior, or indirectly it is called as a Rolle's law right now. It is called as the what? The minimum azeotropes. And that is the meaning of that one is the boiling point of the liquid mixture, that is called as azeotropic mixture. AM is also called as here azeotropic mixture, is less than the BP of the individual liquids. Individual liquids. What's the meaning of that here? Why it shows a larger positive deviation means that because the BP of the liquid mixture is found to be lesser. Liquid mixture is now also called as what mixture here? Azeotropic mixture is found to be less than the BP of the individual liquids. It is called as minimum azeotrope. Similarly, the BP of the liquid mixtures, that liquid mixture is also called as azeotropic mixture, is greater than the BP of the individual liquids, then it is called as a maximum azeotropes. So for example, BP of ethanol C2H5OH and BP of H2O. So it is 78 point something in the form of Kelvin. It is converted as, for example, ethanol is 351.3 Kelvin, and we know that it is 100 degrees Celsius, means it is 373 Kelvin. But the BP of 95.5% of ethyl alcohol plus 4.5% of water, it is indirectly called as rectified spirit, that we will discuss in the alcohol chapters. That is, the 95.5% of ethyl alcohol and the 4.5% of water, when it is calculated, that BP of that resulting mixture is found to be 351.1 in terms of Kelvin. So what's the meaning of that here? This is called mixture. That is 95.5% of ethyl alcohol and 4.5% of water is called as first what mixture it is? Azeotropic mixture, because they boil at a constant temperature of 351.1. But what that 351.1 is? It is less than the boiling point of the individual liquid, for example ethyl alcohol, and then the boiling point of the water. Means the boiling point of the liquid mixture called as a azeotropic mixture, if it is found to be less than the BP of the individual liquids, then it is considered to be an example for a what? The minimum azeotropes. Similarly, we will have another one example in the form of water and HCl. Water and HCl. Water and HCl. The BP of, as usual, water we know that is 373 in terms of Kelvin, and HCl, it is 188 in terms of Kelvin. Whereas the BP of is nearly 80 something, I think. BP of mass of B is actually nearly 80% of 80% of, let us take the HNO3. We will take a separate example related to that. We are calling that as HNO3. It is going to be, instead of HCl, 359 Kelvin, I think. 359 in terms of Kelvin. Okay. Now, the BP of 68% of nitric acid and 32% of water is. So here this boiling point of the azeotropic mixture is found to be around 393.5. 393.5 in terms of Kelvin. So here what is 68% of nitric acid and 32% of water means? It is called, first, what mixture it is? Azeotropic mixture. What is azeotropic mixture? The liquid mixture which boils at a constant temperature without the change in the chemical composition. Means if I distill 68% of nitric acid and 32% of water, means again I am getting the same 68% of nitric acid and 32% of which one? Water, and that temperature is going to be what? 393.5. But what that 393.5 is? It is greater than either the boiling point of the pure water of 373 Kelvin or the boiling point of the pure nitric acid, that is going to be 359 Kelvin. Means the boiling point of the liquid mixture called as azeotropic mixture, if it is found to be what? Greater than the BP of the individual liquids, it is called as what tropes? Maximum azeotropes. Whereas if it is found to be less than the BP of the individual liquid components, then it is called as the minimum azeotropic mixture, or simply it is called as azeotropes. Okay. So this is about the new concept in the form of which one? Azeotropic mixture, which is also called as, simply defining that as the liquid mixtures which have the constant boiling point or constant BP liquid mixtures are also called as what mixtures? Azeotropic mixtures. If the BP of the mixed component or the liquid mixture, if it is less than that of the individual liquids, then it is called as minimum azeotropes. If it is want to be greater, then it is want to be the maximum azeotropic mixtures. Okay. So this completes a solution of liquid in a liquid called as liquid mixtures. First we mentioned the definition, vapor pressure, and then the Raoult's law, and then the types of solutions in the form of ideal solutions and then the non-ideal solutions. Again we have made the difference between ideal and non-ideal. Again the non-ideals are further classified into non-ideal solution showing a positive deviation and a non-ideal solution showing a negative deviation. So on that basis, at the last point we get another term in the form of azeotropic mixture. They are the liquid mixtures which boils at a what temperature? Constant temperature without the change in the chemical composition. Means without the change in the chemical composition means they must have the same which point? Boiling point. So based on that, if the BP of the liquid mixture is found to be lesser than that of the individual liquids, then it is called as minimum azeotropic mixture. If the boiling point of the liquid mixture, if it is found to be greater as compared to that of the individual liquids, then it is called as maximum azeotropes. Okay. Now we left with a solution of S in L. Right now we have discussed the two concepts, that is solution of gas in the liquid. Gaseous solute in the liquid solvent. The second one is solution of the liquid solute in a liquid solvent. Now we left with the last one, that is called as solution of a solid solute in the liquid solvent. Okay. So this is preferably explained with respect to the special type of physical properties of a liquid called as which properties? Colligative properties. The main numericals has been broadly in the form of the colligative properties concept for the solution of a solid with respect to the which one? Liquid. Means the solute is a solid and the liquid is a solvent. Okay. So that all we will discuss in the upcoming sessions with respect to the solution chapters. Okay. So thank you.